This video is going to cover section 8.3 on a population proportion. It's really confidence intervals for population proportions. So, a USA Today snapshot feature stated that 12% of the pleasure boats in the United States were named Serenity. The parameter 12% is a proportion, and that means that of all the pleasure boats in the United States, 12 out of every 100 are named Serenity. So a proportion is a part of a whole, and it can be expressed as a fraction, a decimal, or in this case, a percentage. Proportions can also represent probability. So the probability that a pleasure boat selected at random is named Serenity is 0.12. And proportions can be obtained from samples or populations, just like means. Another example is that during an election year, we see articles in the newspaper that state confidence intervals in terms of proportions or percentages. For example, a poll for a particular candidate running for president might show that the candidate has 40% of the vote within 3 percentage points if the sample is large enough. Often, election polls are calculated with 95% confidence, so the pollsters would be 95% confident that the true proportion of voters who favored the candidate would be between 0.37 and 0.43. So that's taking that 40% and subtracting off those 3 percentage points or adding on those 3 percentage points. So the procedure to find the confidence interval, the sample size, the error bound, and the confidence level for proportion are similar to that of a population mean, but the formulas are a little different. So how do we know when we're dealing with a proportion problem? The underlying distribution is binomial, so there are two choices, success or failure, named Serenity, not named Serenity, favor the candidate, don't favor the candidate. And then there's no mention of a mean or an average. So the symbols that we use in the proportion notation, P is going to be our population proportion. And then this guy is P hat, but sometimes you'll see P prime for our sample proportion. And then they'll go together. If it's P hat, then you'll see Q hat. If it's P prime, you'll see Q prime. And then this is the sample proportion. This is with successes. And then Q is like failures. And so it's 1 minus. Q hat is 1 minus P hat. Q prime is 1 minus P prime. So Q hat is X divided by N. Q hat is N minus X over N, or 1 minus P hat. And X is the number of sample units that possess the characteristic of interest, and N is the sample size. It's for P hat, it's successes divided by total. Q hat, it's failures divided by total. So an example, in a study, 200 people were asked if they were satisfied with their job or profession. 162 said they were. So N is 200, X is 162. So P hat is going to be 162 over 200, or 0.81. So in this sample, 81% of those surveyed were satisfied with their job or profession. So the people who were not satisfied, Q hat, so you can either do N minus X, so 200 minus 162 divided by N, or, which gives you 38 over 200, or you could do 1 minus 0.81. Either way, you'd get 0.19. So 19% did not respond favorably. And again, this is binomial, so P hat equals 1 minus Q hat equals 1 minus P hat, and Q hat plus P hat equals 1. So we can try to estimate the population proportion just like we did with sample means and sample population means. Point and interval estimates for a population proportion can be made using the sample proportion. P hat is a point estimate for P, the population proportion, but we don't know how good that estimate would be, that single number. So that's why we calculate the confidence interval, the interval estimate. So when our sampling size N is no more than 5% of our population size, the sampling distribution of P hat is approximately normal with a mean of P and a standard deviation of the square root of P times Q divided by N. So to construct a confidence interval around a proportion, you use the margin of error, just like with the means, but the formula is different. And now it's the error bound for proportions. So it's the EBP. So it's still the z-score times the standard deviation, but you'll notice it says q hat, p hat, and q hat under the square root. It's because we don't know the population proportions, so we use those point estimates for p and q. So the square root of p hat times q hat divided by n. And confidence intervals about proportions must meet the criteria that n times p hat is greater than or equal to 5 and n times q hat is greater than or equal to 5, which is the total number of successes and the total number of failures must both be greater than 5. So now the specific formula is going to look like this. I know these always look a little crazy, but it's your point estimate, your sample proportion minus your EBP, so the z-score times the standard deviation, with your population proportion in between that and the minus and the plus, the lower bound and the upper bound, just like we did with means in 8.2. And again, your successes and your failures have to both be greater than 5. So here we go. Suppose 250 randomly selected people are surveyed to determine if they own a tablet. Of the 250 surveyed, 98 reported owning a tablet. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of people who own tablets. We can do this in Excel just like we did with the means. We're going to put in our sample size, 250, because we're going to need that to calculate our p hat. Now we need our number of successes, so that's 98. And p hat, remember, is going to be equal to x divided by n. Q hat, you can just do 1 minus p hat. And now we need our z-score for 95%. So remember, that's norm.inv, 1 minus alpha over 2. So if CL is 0.95, alpha is going to be 0.05 divided by 2. And then because it's the normal distribution and the inverse normal formula, we're going to put a 0 and a 1 because we're using standard normal. We get our z-score. Now our standard deviation is going to be the square root of p hat times q hat divided by n. This one's one of the trickier ones that we've seen. So the square root of p hat times q hat divided by our sample size. That is our standard deviation. So the EBP, same as it was before, z-score times the standard deviation. And now our confidence interval is going to be our proportion minus the EBP and then the proportion plus the EBP. So I'm going to do equals our population proportion, our sample proportion minus the EBP. That's going to be the lower limit or bound, and then the sample proportion plus EBP. I'm trying to always say the right words and do something at the same time. It's tricky. We get 0.33 and 0.45. So here we go, walking through the steps, just like we did it in Excel. We can say with 95% confidence that the true proportion of people who own a tablet is between 33.15% and 45.25%. A student polls their school to see if students in the school district are for or against the new legislation regarding school uniforms. They survey 600 students and find that 480 are against the new legislation. We're going to compute a 90% confidence interval for the true percent of students who are against the new legislation and interpret the confidence interval. So same steps that we just did with that last problem. So the first thing we need to know, what's our sample size? 600 students were surveyed. 600 is our sample size. How many were for uniforms? Actually, sorry, we're looking at 480 are against because we want to know the true percent of students who are against the new legislation. So 480 are against. The number is the same. I just said it wrong, so I just wanted to make sure I clarified that. So p hat is going to be 480 divided by 600. And then q hat is going to be 1 minus p hat. Our z-score, norm.inv, 1 minus, so it's a 90% confidence level. So alpha is 0.1, so 0.1 divided by 2, comma 0, comma 1. And our standard deviation. So again, this is the square root of p hat times q hat divided by n. Error bound for our proportion, our EBP, is going to be our z-score times our standard deviation. And then our lower bound is going to be that sample proportion minus our EBP. And our upper bound is going to be our sample proportion plus our EBP. All the stuff we just calculated. And we can say with 90% confidence that the true percent of students who are against the new legislation is between 77.31% and 82.69%. In a sample of 300 students, 68% said they own an iPod and a smartphone. We're going to compute a 97% confidence interval for the true percent of students who own an iPod and a smartphone. So our sample size is 300. So this time I was like, why did I put another example in? Because this time they gave us p hat here. We don't have to calculate it. So I was looking for the number that said that they do own it, but it's not a number. They gave us a percent here. So I can actually just put p hat in here. So 0.68, because I don't know why I said equal. It could just be 0.68. I think I could just type that in. Now, if I wanted to know how many students that was, I would take my sample size and I would multiply it by that percentage. So 204 said they own a smartphone and a tablet. That's our problem, right? An iPod and a smartphone. Who owns an iPod anymore? All right, so we know that p hat is 0.68. So q hat is going to be 1 minus that. Our z-score, super good at these by now. 1 minus 0.03 divided by 2, comma 0, comma 1. Our standard deviation, the square root of p hat times q hat divided by our sample size. And our EBP is our z-score times our standard deviation. So take that 0.68 and subtract off our EBP to get our lower bound, and then take our p hat and add on our error bound to get our upper bound. So we can say with 97% confidence that the true percent of students who own iPods and smartphones is between 62.16% and 73.84%. So we have this thing called the +4 confidence interval for P. There's a certain amount of error introduced into the process of calculating a confidence interval for a proportion. Because we don't know the true proportion for the population, we have to use the point estimates to calculate the standard deviation for the sampling distribution. And studies have shown that the resulting estimation of the standard deviation can be flawed, right? So we use the p hat and the q hat in the standard deviation formula, and that can give us some error. There's a simple adjustment that allows us to produce a more accurate confidence interval. And this is like my favorite, because we just pretend that we have 4 additional observations. 2 of these are successes and 2 are failures. So our new sample size is n plus 4, and the new count of successes is x plus 2. This should be used when the confidence level desired is at least 90% and the sample size is at least 10. So we're going to do the plus 4 method here. Out of a random sample of 65 freshmen at State University, 31 students have declared a major. We're going to use the plus 4 method to find a 96% confidence interval for the true proportion of freshmen at State University who have declared a major. So in Excel, I did this n plus 4 thing here. So you can either take the 65 and add 4, just put 69 in there. Or if you wanted to have the information in, you could always do 65 plus 4. X plus 2, so 31 have declared a major. So you could do 31 plus 2, or you could just write 33 in there. And now we're going to do everything else the same way. So P hat is going to be 33 divided by 69, 0.4782, et cetera, et cetera. Q hat is 1 minus that, 2.17. Our z-score, norm.inv, I did the wrong one. So it's a 96% confidence level, so 1 minus 0.04 divided by 2, comma 0, comma 1. And our standard deviation. So the square root, and this is where this makes a big difference, right? So this is why we're doing this, because this is going to give us a more accurate standard deviation estimate. For EBP, z-score times the standard deviation, and then our sample proportion minus our EBP, and our sample proportion plus our EBP. Using the plus 4 method, we find we are 96% confident that the true percent of freshmen who have declared a major at State University is between 35.48% and 60.18%. Seems like a big interval. So if we need to calculate the sample size, if we want a specific margin of error, we can use the error-bound formula again to calculate that required sample size. And again, it's the minimum required sample size. We're going to use this formula where our sample size is equal to P hat times Q hat times the z-score divided by the error bound for the proportion squared. So this is very similar to the one that we saw for population mean, but these guys aren't squared because they were square rooted. Once they got squared, they're just P hat times Q hat. So that's one of the big differences here. Round up to get a whole number. 2 things we need to think about. If some approximation of P hat is known, we're going to use that value in the formula. But if we don't, then we're going to use 0.5 because that value will give us a sample size sufficiently large to guarantee an accurate prediction. So if you know P hat, go ahead and use it. If you don't, use 0.5. So suppose a mobile phone company wants to determine the current percentage of customers aged 50 plus who use text messaging on their cell phones. How many customers aged 50 plus should the company survey in order to be 90% confident that the estimated sample proportion is within 3 percentage points of the true population proportion of customers aged 50 plus who use text messaging on their cell phones? So, hopping over to Excel, what is the error that we're looking for? Okay. So it's 0.03 because we want to be within 3 percentage points. So they say that 3 percentage points here in the problem. So 3 percentage points, that's 0.03. So put that in here, 0.03. P hat, are we given a P hat in our problem? We're not. So we're going to use 0.5. And then 1 minus 0.5 is 0.5. So our z-score, the norm.inv formula, 1 minus 0.1 divided by 2 for our 90% confidence level. And now we're going to use that formula. So, yeah, I put it in here just so you can see it. No, I didn't. So this is equal to P, oh, I didn't do an equal sign, equals P hat times Q hat. And now I'm going to put it in parentheses. Actually, I need the multiplication. Times the z-score divided by the error. And that's what I'm going to square. So 751.5398. So that's our sample size. So we need to round up. So you can just type 752 in this box. I do believe there is a round up Excel command. Let's see what it gives us. Oh, we need to tell it how much to round up, number of digits. So number of digits. I'm gonna have to work on that for you. So 752. All right. Last example, an internet marketing company wants to determine the current percentage of customers who click on ads on their smartphones. How many customers should the company survey in order to be 90% confident that the estimated proportion is within 5 percentage points of the true population proportion of customers who click on ads on their smartphones? Okay, what do we need? What's our error? So a lot of times this is given to us in words, within 5 percentage points. 5 percentage points, 0.05. 0, oh, it didn't go where I wanted it to, 0.05. We're not given a p hat, so we're going to use 0.5. Careful with your decimal places with problems like this. 1 minus 0.5 is 0.5. Same z-score, norm.inv, 1 minus 0.1 divided by 2, comma 0, comma 1. And what is our n? So again, this is going to be p hat times q hat times, in parentheses, our z-score divided by our error squared. So round up, it's going to be 271. We need a sample size of 271 to be 90% confident that the estimated sample proportion is within 5 percentage points of the true population proportion of customers who click on ads on their smartphones. So that's the end of the video for section 8.3 on confidence intervals on population proportions.